Hello, my name is Ruben from Moscow, and together with my friend Rick Ramirez, we're going to be talking about branch and bound. So for this presentation, we have planned what is an upper bound used for, what is a lower bound, what is an upper bound, um, choosing a better lower bound, and at the very end of this, Rick is going to be talking about some state-of-the-art advancements in branch and bound using physics. So he's going to turn a traveling salesman problem into a Hamiltonian circuit problem, and then into an Ising model. And then he's going to show using physics or some quantum physics, some improvements upon branch and bound. So what is branch and bound actually used for, right? So the name of the game for branch and bound is combinatorial optimization problems, right? So basically, you can use branch and bound to solve these type of problems, right? Um, but just like Muhammad Ali, you want to get through them really fast, right? You want to throw your combinations fast. Okay, so to explain the basic idea behind branch and bound, I'm going to use a very simple pathfinding example. So basically our goal here is to get from over to D, and we want to find the most optimal way to do it. Notice that there are a few different combinations to get to D from T, but we want the best possible one. So the basic idea behind branch and bound is that we want to determine a lower bound, use the lower bound as a guide through the combination of branches, and then prune any infeasible branches. So basically, our lower bound it can be described as this is the best that we can do so far. So for example, if we start at T, our best that we can do so far is going from T to V. This is 8, right? This is our lower bound. So you can say that we can do at least this good so far, right? We're gonna go ahead and continue on with this idea. So from T to V, we branch that. Now we have to look at three candidate solutions, 11, 19, and 9, right? So we have to choose the lower bound, which is 9, so the branch from T to A. But I do also want you to notice that we already reached D, right? But this is not our solution just yet. It might be, but it's not. We can't say that it is yet because um, there exists two other candidate solutions which are shorter than this one. Okay, so now we go ahead and branch A. We see that there are two new ones here, and these are tied, and they're both lower than the other ones. So we can go ahead and just choose whichever one we want from these two. I'm gonna go ahead and choose E. But if you notice up here, from E, there are no other paths, so we can go ahead and consider this an infeasible solution. So this means that we're no longer going to consider it as a candidate solution, and we just take it off the queue. So now we see that 10 is our lower bound, TAG. We branch that. So now we go ahead and look again. So we have 11, 19, 15, and 13. We branch TVG. Now we see we reach D. We also reach D here, but we can't say that this is our candidate solution just yet. I mean, we can't say that this is our absolute best solution just yet because there exists this 13 over here, right? So we have to branch this 13. To go ahead and branch this one. Now we see 16, 19, 15, 16, and 24, right? So we see with our lower bound is actually a path from T over to D. So that means that's our solution. We found the best one. So that's the basic idea behind branch and bound. Okay, so this is a program made by MIT, and basically what you can do is test out branch and bound here. So I'm gonna go ahead and do a pathfinding problem from S to G. So I'll go ahead and start it. I selected branch and bound. And what it's doing, remember, it's always choosing whatever the lower bound is and branching that. As you can see right now, it's quite a bit of combinations that it's checking, but it finally found it. So it took us 226 extensions to find a path from S to G. Okay, so as you saw from my MIT example and our example as well, we almost checked every single path, and we also checked paths that were never going to give us a feasible solution. And we did prune one branch, but it didn't help us out too much. So what can we do? We can apply what are called pruning rules, right? And we basically apply these rules to rule out any infeasible branches. We want to prune any infeasible branches. So for example, we already did this with E. We said when we got to E, there were no other path leading from E, so we excluded it, right? We said that this isn't a feasible solution, and we no longer considered it. We essentially pruned it. But this is a pretty basic rule, and it didn't really help us out too much, right? So what we can actually do is we can notice that we reached G twice, one of them being 10 and the other one being 11, right? So if we got to G at 10 steps, we're never going to find a better solution um, from if we get to G at 11 steps than we did when we got to G at 10 steps, right? So also did this with V, right? We got to V with 8 steps, and then we also got to it at 13. We're never going to find a better solution down here than we did when we got to V here, right? So we can basically say that this is a rule, right? We're gonna say that if we see a node that we already reached with a shorter path, consider that path infeasible. And when we apply that rule, we go from a tree structure that looks like this to a tree structure that looks like this, right? Now I'm gonna go ahead and show you what that looks like using the MIT example. Okay, so now that we know how to apply a rule, let's apply it. So here in the MIT program, you can use a branch and bound with an extended set. Basically, what we're gonna do is anytime we reach a node, we're gonna keep track of which one we reach. So if we reach a node, then that means that we reached it with an optimal path because we're only extending our lower bound, right? So we're just keeping track of which ones we visited already. So I'll go ahead and start it and hopefully you should see it's marking the ones it's visited. So just by applying that rule, we went from 226 extensions over to just 38, which is really good. That's a significant improvement, right? Um, there's another way that we can improve branch and bound, and that is with basically making a better lower bound. And we'll get into that in a later part of the presentation. But basically what we're going to do here is apply a heuristic. So we're not going to keep track of the nodes that we visited. We're just purely going to apply a heuristic and therefore making our lower bound better. So you can see we went from 38 extensions over to 13, and we're not keeping track of the nodes right there, right? We didn't apply that constraint. So now if we combine both, we keep track of the nodes we visited and we apply a heuristic making our lower bound better, uh, we will get A star, right? And that went from 13 to 12. Not a huge improvement here, but keep in mind it is a small problem. If this was a much bigger problem, you would really see a drastic change. So some problems can become much harder when you try to apply an integer constraint to them. And this is an area where branch and bound can actually help. So, for example, in this problem here, we're trying to maximize z. And what you do to solve this in the continuous space is basically you take equation 2 and 3, which are constraints, find the intersection of them, and now you have your solution. X is equal to 5.73, y is equal to 2.73. And if you try to apply an integer constraint, you might think that why don't you just take the floor of them, right? It might work, and yeah, it might work, but it might not, right? So this is where branch and bound can help. So basically, what this problem basically turns into once you apply the integer constraint is a combination problem, right? Um, so for example, you can take the CO of x or the CO of y. That won't work because you're out of bounds, right? You'll end up somewhere over here. You can take the floor of x or the floor of y, and you'll end up here at 5 and 2. Or you can take the floor of x, which is 5, and then the CO of y, which is 3, so you end up here, right? You're basically having a bunch of combinations, right? And then you can also go a step further and say that you're going to take the CO of x minus 1 and then the floor of y, right? You can keep this going. It basically turns into a combination problem. And as we know, combination problems can be solved by branch and bound. Um, so the reason that I'm showing this problem is because it has a great upper bound. And what an upper bound is basically you cannot do any better than this, right? So that's basically what it means. So in this problem, when we plug in our x and y values in the continuous space, we find that the solution for z is 22.65. So that means that in the continuous space, we're never getting anything better than 22.65. So in the integer constraint one, we're definitely not getting anything better than 22, right? So 22 is our absolute best. It doesn't mean that the solution is 22, but it means that no matter what, we're never getting better than 22. So let's go ahead and go through branch and bound and see what that looks like. Okay, so to start solving this problem using branch and bound, I'm going to basically choose a random variable. So in this case, I'm going to choose x, and I'm going to branch it using constraints, right? So the first constraint on the left side that I'm going to apply is x is less than or equal to 5. What that basically is me taking the floor of this, and over here I'm taking the seal of this, right? And then I'm applying the constraint for it. And y now is gonna change, right? And what I'm doing at every branch is I'm gonna get the biggest possible y value that adheres to every constraint under that branch, right? So for example, um, on this branch here, what I'm gonna apply is equation 2, and 3, and then this constraint here, right? Similarly over here, I'm gonna apply this constraint, and then equation 2 and 3, right? And given all those constraints, I'm going to find the biggest possible y value, right? Because remember, we're trying to maximize z. So when I do this, I come up with two solutions, but they're not integer solutions just yet. So I have to keep branching, right? So here, right, what happens is I branch, and now I'm going to switch variables because y is not an integer, but x is. So I'm going to go ahead and keep x, but I'm gonna apply constraints to y. Same thing I did here. I'm going to apply the floor on this left side and then the seal on this side, right? And what happens is that I find a solution that works, but I'm not quite sure this is the best possible solution, right? And this becomes my lower bound, right? So here it was 21, and so here now 21. Um, and over here, I find a solution when I apply a constraint of y is greater than or equal to 4. So I find basically that it breaks equation 2, right? So we get, if we plug this into equation 2, we get 49, which is bigger than 45, so it breaks that constraint. So therefore, it's not a feasible solution. And remember, every time I branch, I'm applying a new constraint. So at this branch here, I was applying y is greater than or equal to 4, x is less than or equal to 5, and equations 2 and 3, right? So every branch that I do has to apply to every previous constraint, right? So here we actually don't even need to branch anymore because think about it, right? We have a constraint for x and a constraint for y, right? So these are both less than or equal to 5, or this one's less than or equal to 5, and this one's less than or equal to 3. If I apply another constraint, what I'm basically gonna do is I'm gonna make one of them lower. I'm either gonna make x lower or y lower. And if we know that if I make one of them lower, I'm gonna have a lower solution overall. So therefore, any branch under this will be less than 21 no matter what. But I'm gonna go ahead and branch it just to show you what that looks like. So when I do that, I applied a new constraint, which still holds for every other constraint, right? But now I find that I have a lower z value, and basically this is what's gonna happen for every other value down here. So we actually can prune this branch, and we don't even need to think about it, right? Um, so let's move on. Our new lower bound, or our lower bound is 21, but we still haven't proved that this one doesn't yield a better solution, so we still have to branch this one, right? So now, what's going to happen is that I'm going to switch again because y isn't an integer here. So I'm going to take the floor of it and I'm going to take the seal of it, right? So what happens is now that I do this, I get the biggest, I basically have y is equal to 2, and I get 22 right here, right? So that's the biggest possible solution. We hit our upper bound. We actually can stop here, and we don't even have to check this one over here because we know based off of our upper bound that this is the best possible solution, so we can just take it. But just to show you, over here, again, we find another situation where one of the constraints breaks, right? When we say that y is greater than or equal to 3, what happens is that it breaks equation 2. I mean 3, sorry. And that's pretty much how you solve an integer problem, an integer constraint problem using branch and bound. One of the ways that we can improve branch and bound is to pick a better lower bound. And to demonstrate this, we're going to use the traveling salesman example. Um, so the traveling salesman is basically you want to find the minimal tour going. We're going to start from A in this case. Um, and if we try to apply our basic branch and bound, that means that we're using just our edges as the lower bound. We find that we search the entire solution space, right? Which is not good. We don't want to do that. So clearly we need a better lower bound. This is still a combinatory optimization problem, but all we need is a better lower bound. So to start off with building our lower bound, we're going to do a matrix encoding. So basically the way this works is that let's say I'm going from A to D. I'm going to encode the matrix saying that A, if I start at A, I'm going to go, and I want to go to D, it's going to be 45, right? So basically, start off at at the row, and then you go to the column, and that'll give you the weight of the graph, right? Of the edge. And you might be wondering what the infinity symbols mean. Basically, what this means is that it's kind of a little bit of a cheat. That way, we don't keep going to the same node, right? So, for example, if we start at A, if we want to choose the shortest path, it'll never be the infinity. Therefore, we're never going to go from A to A, right? Similarly with B and B. So basically, the infinity symbols are there so that we don't um, branch or traverse into that node again. Um, so now we're gonna do matrix reduction, and this is all to build our lower bound. So for example, a matrix reduction is, let's say we're starting off at this row. So we've choose the lowest number in this row, which is 10. You grab 10, you store it, and then you subtract 10 from every element in that row, and this is the result here. And then you repeat the process for all of these, right? And at the end of it, you have a cost of reduction, which in this case is 70. Okay, so if you're anything like me, you're probably wondering why are we doing matrix reduction? Why are we encoding a matrix in the first place, right? And the reason is pretty much if you start from A, right? You the shortest possible path you can go to is B. And if you start from B, the shortest path you can possibly go to is A. And the shortest path from C is B, and D is B, right? Those are basically the paths that we're storing here, right? We stored 10 for both A and B, and we stored 25 for both D and C, right? And basically what we're doing is we're trying to show that the shortest possible tour, right, our solution, will never be shorter than the shortest path coming out of each node, right? So the combination of these 70, like we showed last slide, um, will will be shorter always than the solution of the tour, right? So this is kind of like a heuristic, right? And using this fact, we're gonna improve our lower bound. So at each step, what we're gonna do is the matrix reduction. So for example, when we first start the problem, we have this matrix here. And when we do the matrix reduction, we're taking the shortest path of the current state. We update the state at each step. So once we update the state for the entire graph, when we start the problem, we can then branch to whatever branch we want. So let's say we did branch to B, right? What we want to do is ensure that from B, we never go back to A, and from B, we never go back to B, right? So what we do is fill the matrix with infinity symbols, and basically that means that that's never going to be the shortest path because it's infinity. Um, so if you can see here, from A, we're never going back to A, right? So, or we're never branching from A to anywhere else because we started to branch from B, right? So that means that we can never branch from here to, or here to here, right? So we cover this with infinities. And then from B, right, we never want to go back to A, so we cover that with an infinity as well. And then from B, we never want to go back. we can never go back to B. So if we're at C, we can't go back to B, right? That's this situation here. And if we're at D, we can't go back to B, right? So once we do this, again, using the updated state, we're going to do matrix reduction again, and we find a total cost here. So if the total cost, reduction cost here was 45, right? Because we have our 15 times 3. Um, and then we update the state, so that means that we subtract all of these again, and we get 0, 0, 10, 0, 5, and 0, right? So that means anytime that we're branching, we pick B and we branch from there, we're going to use this matrix to do our next calculation, right? So again, let's say from this was a previous one. So if we go from B to C now, what we're gonna do is ensure that we can't go back to A, right? Because while it's not covered by this infinity symbol here on the graph, we still have to complete the tour. So that means we have to go to D. We can't just go back to A. We can't go back to B because B is covered already. And then we can't go from, well, we already covered B to C, so we're going to cover that again. Right, we already have it here. And from D, you can't go to C because we already covered this. We already reached C, so that means if we're at D, we can't go back, right? So that's basically what we're doing. If we do the reduction of this, we have that it is 5, right? So reduction cost is 5. And again, we update the state. Right, so how are we going to use this, right? So our reduction is here in this R, right? So the matrix at N, right, the current path, or the current node that we're at. So at each node, we're going to calculate a cost, right? So each cost will be equal to the previous cost plus the weight of the edge, and then the reduction cost of the matrix. And you're going to see that this is the new addition, and it's going to be a drastic addition to our problem. So, as you can see, it took off this entire branch here, and it took off two other nodes here, and this entire branch here, right? So at each step, again, when we started, we were at 70, right? We just calculated the reduction of the matrix. So that just equals 70. The parent of A, there is no parent, so that's 0. The weight of the edge at A, we're starting at A, so that's 0. But the reduction matrix, the very first one we did was 70. So when we branch, let's say we go to C, we start at C, we take the parent cost, which is 70, add it to the weight of the node, which is 50, and then do the reduction of the matrix at C, and that'll give us, in this case, 0. Here is 45, and then here again is 0. So it just depends on the matrix. But using this matrix reduction, we found a better lower bound, and it reduced the problem size quite a bit. This is a smaller problem, so you're not going to see like a drastic change, but with the bigger problem, again, it's going to be a much bigger change. And if you notice, we ended up with the same exact solution, this path here, and this is our smaller one. So far we went through 3 different examples of branch and bound. But you might be wondering, when does it become viable? When is it a good idea to use this? We basically think it's down to 3 things. If you have a good lower bound, plenty of constraints, and your problem is a combinatorial optimization problem, then you could use branch and bound. But you gotta remember that depending on how good your lower bound and how many constraints you have, it'll drastically improve performance or decrease performance, right? So if you have a really terrible lower bound, you probably shouldn't use this. If you have very few constraints, probably shouldn't use this as well.
So now that we have a grip on what branch and bound is, I want to focus on how we can increase performance. There are 3 areas of interest that have a significant impact on performance. These include the branching strategies, your searching strategies, and your pruning rules. I want to focus on the searching strategies in the form of a quantum walk and show how we can use this to quadratically increase the speed of our framework. And to do this, I'm going to use the techniques that we learned in class by transforming the traveling salesman into a Hamiltonian circuit and from there transforming it into something called an Ising model, which is a new NP-complete problem that we haven't seen yet, but in this form will allow us to perform the computation on a quantum computer. So let's analyze the solution to this instance of the traveling salesman. The solution is the traversal 2310 and a total distance of 18. We can represent this as a matrix like this, where I corresponds to each vertex and P is the position in the traversal. So since 2 comes first, we put it here, followed by 3, then 1, and then 0. Now the total cost of this traversal can be expressed like this, where W is the distance from node I to node J, and this term here is plus 1 if the path is actually taken. So now if we look at this matrix here, we'll notice that there are constraints associated with it, that if we sum across a row, we get 1, and if we sum across any column, we also get 1. And we can apply these constraints to our cost function to produce a Hamiltonian circuit, where this term here means that each city can only appear once in a traversal, and that each position in the traversal has to be occupied. If either of these are violated, this term A is set to be very large so that the entire cost is thrown out, because we're trying to minimize this thing. Now, with the cost figured out, all we need to do is turn our matrix here into a vector like this, where each row is going to correspond to an element within my vector. So this first row here will be assigned to x1, and then the second to x2, and so on, to produce this vector and the corresponding value that goes with it. Okay, now finally all we need to do is change variables from x to 1 minus sigma over 2, and I'm going to call that h, and I'll describe what sigma and h are a little later, but for now that's all we need to do to prepare the traveling salesman. Now we need to talk about something called the Ising model. This is a problem from physics that is used to model ferromagnets. However, it's been found to be useful in solving combinatorial optimization problems, and it turns out that at least for the two-dimensional case that it's NP complete. So what the problem is that we have a material where all the atoms within this material form a lattice, and each atom can have a spin associated with it. It can have either a spin up, represented with this symbol, or a spin down by this one, and graphically like this. Now, the question is, what is the energy of the system? So, we can calculate for each individual particle the energy associated with the spin configuration with this equation here, where J is a coupling interaction and sigma sub k is a discrete variable that we assign either +1 to if it's spin up, or -1 if it's spin down. So to calculate, say, the energy of this particle here, all we do is take the spin states, multiply them together, and then sum over for every neighbor. This symbol here means to sum over the nearest neighbor. So the energy associated with this particle here is -2J. And the energy of the system is just the sum of all the individual energies. These spins, they're not locked in place. Like, they can flip. We can force them to flip by introducing a magnetic field. If you increase the strength, eventually, these spins, they want to align with the field. So eventually we could get this spin down to flip up into the z direction. But, that's going to change the energy. So to calculate the energy in the presence of an external magnetic field, we use this equation here, where G sub S and mu sub B are constants, B is a magnetic field, and we orient our frame of reference into the z direction. And those discrete variables from before, those sigma sub k, we change them into now sigma sub z, which is something called a poly z operator. And the effect of this thing acting on, let's say, like a particle that's in a superposition of spin up and spin down would look like this. Now, as time goes on, the system will eventually restabilize into a new ground state energy. And the situation is analogous to these metronomes on this board here, where the board is acting like the coupling constant J, and eventually you see they start to synchronize, and that corresponds to a ground state energy. And we can calculate this using this equation here, called the Schrodinger equation. This is the time-independent version of it, where we take our Hamiltonian from before this equation and apply it to a vector to give us a scalar times another vector. So it's the same vector, just scaled differently. And it turns out that the solution to this problem is equivalent to our traveling salesman problem. Because if you remember from before, we transformed our solution into this vector here. This eigenvalue is going to correspond to a set of eigenvectors, and if we assign it to the minimum eigenvalue, will give us the configuration for the optimal path for the original problem. And the cost function we modeled after the Hamiltonian, and like even if you look at the Ising Hamiltonian, you can see like the similarities. Like it's not far off to realize that solving this problem could solve the traveling salesman as well. Now the question is, why go through all this trouble? You'll find a lot of papers online converting NP-complete problems into this Ising model, and for good reason. This model is ideal for quantum computation. So let's take a look at the classical complexity for the branch and bound framework. So if we remove nodes according to our available pruning rules, we find that the size of the truncated tree is T min, and that to find any particular node within the tree is on a complexity of the order of the size of the truncated tree. Now the quantum version of this technique uses the same bound and cost subroutines as the classical model. However, according to this paper here, it's possible to increase the performance by this amount here, where D is the depth of the tree and Cmax is the maximum cost, both of which are taken to be much smaller than T. This is their algorithm, and the speed increase is coming from this function here, their searching function, which is capable of finding a marked node in a tree in a time square root of n, as opposed to on the order of n for the classical model. Okay, so that pretty much sums up all the major points that we wanted to cover. This topic, it tends to bleed into a lot of other techniques, and the differences can become kind of blurry, but I hope we were able to make it clear of what branch and bound is and when it's appropriate to use it. If anything was not clear, we're adding links to the source material in the description, and of course, you're welcome to message directly if you need clarification on anything. Okay, so good luck to everyone in 5300, and if anyone else is watching and has feedback for future videos, that would be very much appreciated.